haven't recorded one in a long time. Could be fun. Okay, so yesterday I introduced you to something called valence bond theory. And this is the theory that we now use to explain bonding. And we now think of a single bond as being an overlap of atomic orbitals. And I've asked you to think of that single bond as now being called a sigma bond, which represents this end-to-end overlap of either s orbitals or p orbitals, or even an s and a p orbital. D orbitals, do they undergo sigma bonds? They may. It's definitely not part of this course. In order to have bonding with d orbitals, you're now into the transition metals. Do metals form bonds? They can. They're not just ionic in nature. I mentioned the other day about how iron can form bonds with the protein in hemoglobin in order to make that hemoglobin molecule, and it would use its d orbitals, but we won't be discussing that in this course. Okay, so as we continued on, I got to the point where I wanted to talk about CH4, all right? So methane, a carbon bonded to 4 hydrogens, and we wanted to talk and address the situation of that. Now, if we were to look at carbon here in its atomic configuration, we would see that carbon has 2 electrons in the 2s orbital and then 2 electrons in 2 of the p orbitals. And now we're going to attempt to attach 4 hydrogens to that. Well, I'm hoping that you can see that there's an issue with that, because this orbital is already full, and therefore I can't put any more electrons in it. So to share an electron with it is not possible according to the Pauli exclusion principle. I can overlap something with this one and this one, but that would only take care of 2 hydrogens, and therefore we've got a problem with the idea of overlapping with just regular orbitals found in the carbon atom. There is a second issue as well. When we look at the carbon with 4 hydrogens, the methane molecule, all right, I'm pulling out a model right here for those who are listening, we get this particular shape. Now I can show you that on the computer. If you go to Google Classroom, all right, I have on the About page a neat little online molecular model builder, which we might be using in the near future when we do our molecular geometry yoga. I might have you put your molecules on here. But this is a neat thing. You can play around with this. It works on your phone. It works on mobile. It works on all kinds of different things. So this molecular model view, here I'm clicking, I'm able to rotate a molecule, all right? This is a caffeine molecule. I don't know why it seems that whenever a chemistry person builds a molecular model viewer, they like to start with caffeine, maybe because it gets them through the day, who knows. Anyway, so what we can do here is I can take that molecule and put it in the garbage, and then I can grab a carbon, and I can put that carbon right there on the workspace, and then I can add H's to that particular thing right there. And if I click on that, I'm going to add H's to it. Come on, add the H's. And I can zoom in and I can make a CH4, all right? Now at this point, I'm going to pause my recording. So that's kind of a neat little program. Now, if I click over here, I got to drag it over to the right. If you're using it on your phone, you can just drag it over, and you'll notice 2D to 3D, and if I click on it, it's going to now generate the 3-dimensional model of a CH4 molecule. Now, the reason I brought that up, because people watching the video can't see what I'm holding up here, but this is the shape. This is what we see when we look at a methane molecule. Now, you might be asking, how do we see that? They're so small. Well, chemists and physicists have ways of looking at the positions of atoms in molecules. It's a particular process called X-ray diffraction. They can also use neutrons to do this, neutron diffraction. And what they do is they shine X-rays at a solid crystal of whatever molecule that they're dealing with. So sometimes it has to be very cold. It does for methane. And as the X-rays sneak in between the atoms, they spread and they interact and they diffract. If you've taken physics with Mr. Petrus, you would have learned about interference and diffraction, and the fact that light can spread out and diffract as it goes through a small slit. Well, the atoms within the crystal behave as if they're small slits, and so they will spread out and make a characteristic pattern. As you know from your physics, if you've taken it, you can then measure the separation between the bright and dark spots. You can calculate in reverse how wide the separation of the slits are. They do the exact same thing, except by working their way backwards, they can determine the position of the atoms and their distances from each other. That allows them to get bond lengths, and it allows them to get actually very accurate structures of those molecules. So when physicists and chemists look at this molecule, they see a molecule that is this shape. We call this shape a tetrahedral shape. A tetrahedron you can think of like a tripod with a camera sticking out the top, right? So there we've got our tetrahedral shape. Now, in order to get a tetrahedral shape, we need to have the orbitals at very specific angles. They have to be exactly at 109.5 degrees from each other. In a regular p orbital, well, you tell me, what's the angle between two adjacent p orbitals? What's the angle between two adjacent p orbitals? Which way does one of the p orbitals go? Well, we'll go up and down. Pardon for the yellow, hard to see. Where's the next p orbital go? What was the orientation when we drew that yesterday? This is all being recorded for online purposes. Your silence is indicating your lack of knowledge, really. So you want to be on the ball. Which way does the next p orbital go? One is up and down. Where's the next one? Horizontal, right? Left and right. So I've got one over here. Zip, zip. And where is the last one? So we got X, we got Y. Coming out of the board, Z. So it's coming out in front, and it's kind of hiding in behind like we drew yesterday. What is the angle between adjacent p orbitals? I just need an angle. Jenna? 90 degrees, thank you. 90 degrees. But when we look at this structure, we know from X-ray diffraction, it's not 90 degrees, it's 109.5 degrees. So even if we attempted to bond two hydrogens to these lone electrons, they should orient themselves 90 degrees from each other, and we don't see that. So something is going on. So what do chemists and physicists do when they don't see what their theory predicts? They create a new theory. They create a new idea. And the new idea to explain this is called hybridization theory. And I already had you write that down. And this theory, again, treats orbitals as if they're waves. Well, because they are. So we can do that. So what do they do? Well, because each of these orbitals, each of these things on our chart are mathematical representations, we can use different equations to produce different shaped orbitals. All right? Remember I said they chose these equations because they reflect what we see. So what did they do? They, in theory, mathematically put all of the four orbitals, the 2s and the 3,2p, you can imagine that they put them into an orbital blender. And they put all of the mathematical equations for all four waves into one equation. And then they removed four orbitals that were identical to each other. In other words, they took that big equation, which came from adding the 2s equation to the 3,2p equations. They divided it by 4, so 4 identical orbitals would come from it, And when they did that, it produced 4 orbitals that oriented themselves exactly in this tetrahedral shape. So we now call them hybrid orbitals. A hybrid is when you take 2 or more, things or properties from individuals and you put them together into one individual, and you have now the mixture of properties of those individuals. So we get a hybrid orbitals from putting those orbitals together. The reason we like this theory is because it works. It explains what we see. So what we do is we create hybrid orbitals, and I do want you to draw this. I don't know if you did yet, and I've got to add to this. So we have our, and I'd like this to be black. We have our 2s orbitals and our two 2s electrons and our 2p electrons. That makes 4. And then as atoms approach the carbon, so as the hydrogen atoms are approaching the carbon to form bonds, the carbon hybridizes. It starts out as a regular atom, like we know, and as the hydrogens approach, they form hybrid orbitals. I like to imagine it as if it's a transformer. Transformers? No? That used to be big a couple years ago, the movie Transformers? No? We like Transformers? Kids love Transformers. All right, anyway. So something takes place. The energy of the approaching other atoms that are going to form bonds transforms the atomic carbon into the hybrid carbon. We need to give these new hybrid orbitals a name, and we call them sp3 orbitals because they're made up of 1s and 3p orbitals to form 4 identical orbitals. Notice how I put the s orbital down here, a little lower, and then the p orbital up here. And then on purpose, I've put the sp3 orbitals somewhere in between them. If you didn't put it like that, it's not a big deal. But the energy level of the sp3 orbitals will be somewhere between the s and the p because it's a mixture of the two. They'll actually be a little closer to the p because they're made up of 3 parts p and 1 part s. All right, so it actually makes them energetically a little closer to the level of the p orbitals. But now, because they're all on the same energy value, those electrons will spread themselves out, just as the Hund's rule states, and we will have 4 half-filled sp3 orbitals that are ready to bond. Okay? All right? So that's what hybridization theory is. It allows for the changing of the atomic orbitals to become hybrid orbitals to accommodate the bonding. Okay, let's take a look at then some pictures of this. Oh, this is just again a graphic representation. So there's the S, there's the P's. You put them in the mathematical blender, you divide by 4, and you get these, one going up, one coming out on an angle, one leg of the tripod, another coming out on an angle in behind, one coming in between here, and you have this kind of tripod with a camera on the top orientation. All right? It's true that they've got a second lobe on the back end. It's true that there is a second lobe there, just like the P, but because of the S's sphere, it makes one of the lobes more like a bigger bulb, and the bonding takes place only with that big lobe. So when I draw these orbitals, I'm not going to draw these little lobes in the background. I'm going to ignore them because bonding never takes place on those because they're so small. The bonding only takes place on the larger ones. Okay? All right. So let's do some examples. And I was going to use Smart Notebook, but no, I guess I can use this. This is exciting. I'll use this, not a problem. And now I'm going to change things. Actually, no, I will go to Smart Notebook. It'll be a little easier. It's the same thing. You're going to write down It's CH3, so I'm going to go down to CH3. I got to go to my pages. Which one is CH3? Let's go up one. Previous, sorry, CH4. CH4, there it is. And now I'm going to start with the Lewis diagram. So I'm going to start with Lewis. I'm not going to start with an electron dot diagram. And I'm hoping that you guys know how to draw the Lewis diagram for CH4. We've got C, oops, I got to activate it. C, H, 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 H. All right? Okay? Now the energy level diagram. Now for this energy level diagram, I'm going to draw carbon as the regular carbon, and then I'm going to draw it as the hybrid carbon. I'm not going to do that for subsequent examples. We'll go straight to the hybrid version. But for this first one, carbon normally looks like this, right? If we go back to the previous noble gas, we're going back to helium. Again, we've got 2s with 2 electrons in it, and then again, I've got 2p with 2 lone electrons in it. Well, as the hydrogens come in, we're going to have hybridization. Carbon, again, the core of helium. 1, 2, 3, 4. I just draw them as ovals, and I write underneath them sp3. And the 4 electrons are now evenly distributed, and pardon the orientation, 1, 2, 3, 3, 4. That's horrendous. I apologize. There's 1 electron in each of those. 1, 2, 3, 4. Okay? Notice S, P, P, P is 4, and that's why we have 4 ovals there. We're going to learn about different hybrids a little later on, and that's how we're going to tell how many ovals we need. Now we've got 4 identical orbitals, and now we can start overlapping our H's. I'm just going to put an H as a circle up there, okay? 1s. That's one of our H's right there. It's going to be end-to-end overlap. It's going to be a sigma bond. I'll put another one up there. It doesn't matter what side they're on. Again, that's a 1s. That's going to be a sigma bond. Again, 1s. That's going to be a sigma bond. And again, 1s. And that's going to overlap with that, and that's going to be a sigma bond. 4 sigma bonds. Now, you'll notice I went underneath my 3D Lewis. I'm gonna need some space. I can do that over here to the right. I'll have enough room. You guys can write your 3D Lewis wherever you need to put that. Okay? All right. Now the fun part. Now for the orbital view. We need to draw a tripod. How are we going to do that type of thing? Well, it's not too bad. So let's get some good colors here. Let's get a dark color there. Oh, why did it do that? Why are you doing that, you silly program? Change that to red. Is it going to be red? I'm going to put one up here. It's not red. It's a piece of junk. Let's go over to here. That's going to be yellow. I don't want yellow because yellow you can't see. What's this? Well, we'll try this one. Up. There's one of them. There's the up orbital. Okay? Now I'm going to draw it as if the 2 legs of the tripod are pointing out at you. Okay? So now I'm going to put one that is out front, right there. That's one of the legs coming out front. And I'm going to put another one out front, right there. There's the other leg out front. Now that's supposed to be the same size, but my eraser doesn't work very well. So there's the 2 coming out front. Now the third one is hiding in behind those 2 legs. So I like to draw it, and I think this is going to be yellow, and yellow's no good. I'll draw it as a red again. This guy is hiding in behind there. You see how that other leg is hiding in behind? Okay, see how I did that? And now we're going to have 4 of those hydrogens bonded on those guys like that. and there's going to be 2 electrons in each of those overlap positions. Those are all sigma bonds. Okay? You can probably do it all in pencil. I don't know how artistic you are. Look how tiny. Ooh, that's fun. Such a tiny picture. Okay. All right. There is our sp3 hybridized carbon to make a tetrahedral shape, okay, and to then result in 4 identical sigma bonds. We're going to gather up more information a little later on about this, but the angle in between here, actually I won't put that angle on there. I'll write it later on. The angle is 109.5. When we write some more details about this sp3 hybrid, we'll write those details out then. What I want to now do is introduce you to something called the 3D Lewis diagram. So we've been drawing Lewis diagrams up to this point as if the molecules have been squished onto the board or onto the surface, flat as can be. But we now know the molecules actually have 3-dimensional shape. So we'd like to, in a Lewis diagram, represent that 3-dimensional shape. So I'm going to start with the carbon at the center, and I'm kind of representing the 3-dimensional shape in that orbital view. I'm going to go up with my 1 hydrogen, okay? And now I'm going to rotate my tetrahedron a little bit. I'm going to rotate it so that the other hydrogen is flat on the board. This one here to the right. So my other one comes out like this. There it is. So now I've got 2 hydrogens. That one is going to be coming out of the board, and the other one is going to be going into the board. And we have to represent that kind of 3-dimensionally. The way we do that is, for the one that's coming out of the board, we draw the bond as a wedge. See how I've drawn it as a wedge? Like a wedge getting fatter? And we fill it in. And this is not going to work very well on the smart board. Actually, that didn't work too bad. Impressive. Why do we use a wedge? Well, if I were to take this meter stick, all right, and I were to then try to poke you in the eye, that part of the meter stick that's closer to your eye is going to look really fat, isn't it? But the part of the meter stick that's far away from your eye is going to look smaller. What do they call that in art? Some perspective diagram or something? Anybody do art? No? You see them sitting in the hall and they're looking down the hall and they're drawing all these lines. You know what I'm talking about? See how that looks fat and that looks thin? So this makes the bond look 3D. Ooh, no, nothing? All right. So that's exciting. This turns this chemistry class into 3D. Awesome 3D. I should make you wear glasses. Nothing. Not a thing? That's funny stuff. I usually get some laughs out of that. Come on, not even kill. Okay, so how do we do the one that's going in behind? We use kind of like a zigzag motion with a reverse wedge. I can do it better on the board. I'll first do it on the board. So here's the one coming out in front, right? There's the other guy, there's the other guy. And you start with a fat wedge and you do a zigzag, zigzag until it disappears. You see how I kind of did a zigzag, zigzag until it gets smaller? Zigzag, zigzag, zigzag until it kind of disappears and goes away from us. So the zigzag represents that it's going in behind. Zigzag, 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 smaller, smaller, smaller. Like I said, it didn't work so well on the smart board. And you know what you can do? Draw that H a little smaller because it's further away. It's in behind. So that's how we draw a Lewis diagram that represents a tetrahedron. That's exciting. That means we now have a better representation of the molecule that is the tetrahedron. Okay, let's do another example. Click. Let's jump ahead to, no, let's do NH3. Let's do NH3. Okay, so now I'm going to introduce you to a new little notation here. Drawing the Lewis diagram for NH3. N, H, 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 and it looks like that, right? We're okay with that. I hope everybody got that. Now I'm going to show you how we know what type of hybridization it is. You might think, we only know one type of hybridization, Mr. Sanders. You've just taught us only one. But there's about 5 different types of hybridization I'm going to teach you. So we need a way to be able to distinguish it. So what we do is we analyze the central atom. So I put a squiggly arrow pointing to the central atom so it doesn't look like a bond and it doesn't look like a reaction. And I'm going to analyze that atom right there. And I'd like you to write that on there. So I want you to put a squiggly arrow so that we can analyze what that atom is doing. And what we look at is we look for 2 things. We look for how many pairs of electrons there are on that central atom. We look for bonding pairs, and we look for lone pairs. Bonding pairs are only made up of sigma bonds. That's going to become important tomorrow when we talk about double bonds. For today, bonding pairs, you're just counting them, but I'll tell you how you take care of them later. 1, 2, 3. There are 3 bonding pairs on that particular atom. Now let's look for lone pairs, pairs that are not taking part in bonding. There's one lone pair on that one. That means in total, this particular atom needs 4 pairs of electrons. It needs 4 places to put electrons. It needs 4 identical orbitals. And I've just taught you that if you need 4 identical orbitals, you need an S and 3 Ps. So because this number is 4, we can say that the hybridization is sp3. So the fact that it's 4 is sp3. Later on, I don't know if I'll get to it because we're going to get that visit from the health nurse. But later on, if we only need 3, well, we're only going to need S and 2 Ps, sp2 hybridization. And if we only need 2, we're going to need S and a P, sp hybridization. And I'll teach you about those shapes later on. Okay, so we've got 4 of these things. It means I need sp3, which means I can go straight to the sp3 hybridization. Yes, it's helium. But because it's sp3 hybridized, I'm going to draw it with 4 ovals because the S and the 3 Ps have been mashed together in a hybridization situation. 1, 2, 3, 4. Now, how many valence electrons does nitrogen have? Well, it's got 3 that it used to have in the P, and it's got 2 that it used to have in the S. So it's got 5 valence electrons. We still have to distribute those 5 valence electrons. 1, 2, 3, 4, 5. And now we see that there are 3 unpaired that are available for bonding. So we're going to put some H's with that. Again, you'll notice I'm not even putting the H anymore because really I just want to signify that we're getting overlap and it's a sigma bond. 1s, there's 1 electron in it, a sigma bond. 1s, there's 1 electron in it, a sigma bond. Exciting. So what does that mean? Well, now we need, because it's sp3, we need a tetrahedron. I guess I'm jumping the gun a little bit. As soon as we know that it's sp3, we can designate it something called the EPA. And I'm going to define EPA in words a little later on because I'm watching the clock. I have no idea when we're going to get our visit. But EPA stands for the electron pair arrangement. What shape are the electron pairs arranged in? Well, if we have 4 identical, and if it is sp3, it is always this shape, which we call a tetrahedron. So this is tetrahedral, A-L, tetrahedral. Again, a tripod with the thing on top. Why is it called a tetrahedron? If you were to connect all of the faces of this with triangles, you'd get 4 identical triangles on each face. 4 is tetra. It's a 3-dimensional shape made up of triangles that are identical. It's a tetrahedron. That's why it's called a tetrahedron. But because we're more interested in the way the bonds are going, I'm more interested in the tripod with the camera on the top. I'm not interested in the faces. Okay. As soon as you know it's a tetrahedron, we can draw our orbital tetrahedron just like we did for the last one. One sticking up top. And I'm going to use the yellow. I apologize. It's so bright. It's hard to see. Let's put that one to the right. And let's put this guy to the left, right? And let's put the blue one in the background. And notice in our energy level diagram, I have one that's full, can't bond, and then I'm going to have 3 that have circles on it. Which one would you like to be the lone pair? Which one would you like to be full of those 4 orbitals? It's up to you. Which one do you want? Actually, I want you to pick a certain one. Which one's most logical, do you think, to have that's full? Nobody. Nothing. Mr. Sanders, I think the top one would make good sense to be full. Well, that's exactly correct, Jimmy. Nice job. All right. Let's make the top one has the full orbital. Goodness, you guys sit there. That's funny. So, that guy's full. Lone pair at the top. They're all looking at me. Mr. Sanders is losing his mind. And you'd be correct. Pair there. Pair there. Okay, so there we have it. Like so. 3-dimensional Lewis diagram. It's going to look just like the other one, except now we're going to have a lone pair in its position. Now, I'm going to start with the nitrogen at the center, obviously. Terrible N, by the way, but anyway, I'm not going to erase it. And again, I'm going to put all of them on there. Up, off to the side, wedge coming out front, kind of scribbly inverted wedge going in back. And now, instead of putting a hydrogen at the top, I'm just going to put a couple of dots there. Now, normally when we get rolling, you wouldn't put a line there. It's not a bond. It's a lone pair. But I just want to give you guys kind of a sense of, the fact that we're using the same shape. And actually, on my next example, we won't put the line in there. I'll tell you how we adjust for it. But that's how we're dealing. So now we just need H, H, H. All right. Let's do one more example, and then we'll talk about the other types of hybridization, hopefully. So, good old water. So again, hopefully we're going to start doing the procedure without waiting for me. Draw the Lewis, do that squiggly line, analyze the central atom. Check to see how many bond pairs there are, which are the lines. Check to see how many lone pairs there are. And let's see how many orbitals we need to fulfill this structure. Doesn't matter where you put the lines. If you put them on opposite sides, it doesn't matter. This is just a good old-fashioned regular Lewis. We've squished the molecule onto the board. We haven't really looked at the 3-dimensional structure yet. 2 lines coming from that oxygen, 2 bond pairs, 2 lone pairs. I've only taught you one type of hybridization so far, so it's going to have to be a 4. But in the future, it could be a 3 or a 2. 4, therefore, sp3 right away. SPPP. I need 4 of them. And hopefully you're memorizing that the EPA is, because there will be different shapes for different hybridizations, but in this case, what word have I been using to describe this? Yep. tetrahedron or tetrahedral shape, or tetrahedron is fine. Either or. Tetrahedral. I have to say it like that or I spell it wrong. So many letters. Such a long word. So for the energy level diagram, I need 4 ovals. SPPP. I need 4 ovals. That's what it tells me. That's what that Lewis diagram tells me. That's kind of handy. Our Lewis diagrams are guiding us to the hybridization. O, back to helium. 1, 2, 3, 4. You can put sp3 underneath. I don't know if I did that last time. How many valence electrons in oxygen? And we need all of them. We need the S1s and the P1s because we removed them, we hybridized, and now we're going to redistribute them. Mr. Sanders, there's 6 in oxygen. Thank you again, Timmy. That's excellent. You provide me with the most answers of everyone in this class. Good job. All right. 1, 2, 3, 4, 5, 6. So you can see we've got 2 that are filled. Nice, that's the lone pairs. We've got 2 that are not filled, and so we need 1s of a hydrogen to fill that. That's a sigma bond. 1s of a hydrogen, we can fill that. That's a sigma bond. We're going to need a tetrahedron, which means we can go right to the orbital view. We can draw our little tripod. 1 up there. 1 off to the side, 1 out front. Oh, they should be the same size, I apologize. 1 hiding in behind. And now 2 of these need to be filled. Let's go with that one. And actually, I should have maybe did that differently. I would like to erase. I wonder if I can erase that without erasing the whole world. Nope. Ooh, can I erase that thing? Whoa, cut. Are you kidding me? What's going on here? Cancel. Cancel. Oh, man. Okay, let's leave it where it is before I completely mess up the whole world. Let's put another lone pair. It doesn't matter. Let's put it over here, and then I'm going to put a loop in here. There's 1 there, and there's 1 there. All right. Now, for the 3D Lewis, and I'm going to now talk about ignoring the lines where there are lone pairs. Oxygen. And I'm going to put 1 hydrogen up here because it's easy to draw the line that's flat on the board. And I'm going to put the second hydrogen over here because it's also flat on the board. My next 2 lines need to come out and go in behind, but guess what? They're lone pairs now. So we don't even need to worry about drawing a wedge or a squiggly squiggly. We can just put dot, 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 dot. 1 lone pair coming out. 1 lone pair going back in. And so the shape of that water molecule, it's not 90 degrees. It's a bent shape. It's just got a little bend to it, like a boomerang. Okay? All right. Now, I did have some other examples here. Let's move on to the next slide. The C2H6, but I'm running into issues. So what I want to do now is go back and talk about other types of hybridization. And then I think maybe we will be, where did I put that thing? What the, right there, CH4, advanced, 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 advanced. Oh, by the way, you now have the ability to do worksheet number 1, which just has some molecules on it that you can draw, okay? And that's on the day's work page. It might even been on yesterday's day's work page, okay? And now what I want to do, hopefully to finish off today, is just talk about different types of hybridization, all right? So write down that other types of hybridization. Let's first start by taking note of the first type of hybridization that we've learned. And actually, we're not going to, don't write this picture down. I'm going to draw an orbital view down here the way we were drawing it. I don't like the way that one works because it's hard to see the different angles, okay? So don't worry about drawing that. We'll draw it the way we want it. But I do want you to draw sp3. I want you to draw the original. Notice I didn't put any designations for those, because this could be for something like sulfur. It might be 3s and 3p. It might be something like selenium, right? 4s and 4p. All those different atoms can undergo that different type of hybridization. The key is I want you to take all 4 of these and turn them into 4 hybrid orbitals. Here I've now defined EPA, electron pair arrangement, and it's tetrahedral. And to finish off, I'm going to draw on our orbital view. So again, 1 up here, 1 off to the side. Apologize for the yellow. 1 off to the other side. And we'll draw 1 hiding in behind. But what I do want you to add to this is a line going up the middle of this guy. I know I'm semi-rushing. I apologize. It's not crazy rushing, but it's a little rushed. And I want you to draw a line going down the middle of this guy, because in here I'm going to define our angle for this particular shape. And you can see it right there. It's 109.5 degrees. That number will be something that you're going to, if you continue on with chemistry, especially organic chemistry, you're going to see that over and over and over again. All right? So tomorrow I'll continue with the rest of the hybrid orbitals. You're exactly perfect, a perfect timing. I just need to shut this down. I'm actually recording this lesson because I got some kids away. Where's my recorder? There it is.